So to find epsilon R of a material can be found using 1 plus xe, or by dividing the total permittivity divided by the free space permittivity. Now, in order to measure epsilon R experimentally, how we find epsilon R experimentally? By using a parallel plate capacitor. Okay, we will have parallel plate capacitor. Okay, and this parallel plate capacitor is connected to a certain source, with this is a plus terminal and this is a negative terminal, so the electric field will establish between the two plates, and this parallel plate capacitor will be connected to a capacitor meter to measure its capacitance. Now the capacitance for a parallel plate capacitor, it is equal to epsilon times area divided by the distance between the plates. So in the lab, we will fix the distance between the two plates, say for example 1 centimeter, and we make the material, for example, air at the beginning, and we measure the capacitance for air, let us call it as C node, equal epsilon node times S over D. Now, if we put a material inside, a material with unknown epsilon R, we calculate the capacitance another time. The new capacitance will equal to epsilon node times epsilon R times S over distance. So if we divide C divided by C node, this is equal to epsilon R. This is how to find epsilon R for a material experimentally. Now for the topic talking about dielectric breakdown. What are the factors that will ease breaking down the dielectric? We should know these factors in order to avoid breaking down the dielectric. If you are using dielectric as a battery, you don't need to breaking down this dielectric to avoid shorting the plus plate to the negative plate. So the breakdown depends on many factors. These factors are nature of the material, nature of the dielectric material. Once we said about the classification of materials, we said it can be classified into conductors, semiconductors, dielectric. And in the dielectric, we said that sigma for dielectric much less than 1 and greater than 0. There is no negative conductivity. Some of these dielectric are very close to 1. Say for example 0.8, 0.9. These materials with appropriate media, it can be easily become semiconductor or conductor. So we have to know the dielectric material that we use, where it is listed within this range. So this is the nature of the material. Second factor, it is the temperature. We know before that decreasing the temperature will increase the conductivity, since there is no thermal energy and every electron will be in its band, no squeezing on one band, no zigzag motion. The current will be large, so the conductivity will be large. Third factor is the humidity. Humidity, if it is increased, sigma will increase. The fourth factor, the applied electric field. If the applied electric field increase, sigma also will increase. Okay, since the current density J equals sigma times E, so we need to apply a certain electric field that the material can handle. So every material has a maximum electric field, and this is called the electric strength. The electric strength means the maximum value of electric field that the maximum can tolerate without being breaking down. So we have to know what is the maximum value we should apply to a material in order to prevent breaking down this material. And the last factor, the time that the electric field is applied. Okay. These factors are studied individually, so in order to know what is the maximum value that the electric can handle, we have to fix the other 4 parameters. We have to choose a certain material under a certain temperature, under a certain humidity, for a certain amount of time, and increasing the electric field gradually until the material is breaking down. The electric field before the breaking down occurs, this is the maximum value the material can tolerate, which is referred as dielectric strength. Okay, now let us take an example about polarization in dielectric. Assume that we have a dielectric cube. So we have a cube made of a dielectric material. This cube has a length and edge length of L, and this cube, it is centered at the origin. Okay, assume the origin is the center of this cube. Every edge is L. So at every axis, the cube will range from minus L over 2 to L over 2 in y coordinate, in y axis, same as x axis, same as z axis. This cube, it is put under an external polarization. It affected by polarization vector P equal A times R, where A is constant and R is the position vector defined as xax plus yay plus zaz. Find all bonded charge densities and the total charge. So all bonded charge densities, it is meant by to find rho ps and rho pv value. So to find the rho ps value, rho ps equal p dot a normal. So we have to work rho ps at each surface. So we have 6 faces. For the front face, this face here, the normal to this face, the a normal, it is equal to ax. So for the front face, rho ps front, it is equal polarization vector, which is a times x ax dot a normal, which is ax, and this is equal to a times x. But the front face located at x equal L over 2, so it is equal to a L over 2 coulomb per meter square. So the total bonded charge distribution at the front face, it is equal to a L over 2 coulomb per meter square. Now for the back face, rho ps back, which is located at x equal minus L over 2, it is equal to p dot a normal. Now the polarization vector is a times x in x direction dot negative ax. This is equal to minus a times x at x equal minus L over 2. So the surface charge, the bond surface charge at that face, it is also equal L over 2 coulomb per meter square. So if you repeat for all faces, you will see that all rho ps equal to Al over 2 coulomb per meter square for all faces, since the position vector xx plus yay plus zaz is identical in all directions. Now to find the total bond volume charge distribution rho pv, it is equal to minus divergence of p, which is equal to, you have to apply the divergence in the Cartesian coordinate, which is partial bx by partial x plus partial by by partial y plus partial bz by partial z. And if you derive the vector p with respect to the coordinate, the result will be a plus a plus a. So rho pv equal minus 3a coulomb per meter cubic. Now to find the total bond charge, the positive bond charge qb plus equal rho ps ds integration over all surfaces. So either we have to first we have to get rid of this circulation by making this as 6 double integral, 1 double integral for each face. But since all faces have the same rho ps, so we can have 6 multiplied by rho ps ds for a certain face, which is equal to 6 multiplied by rho ps, which is al over 2, and since the cube is uniform, which area is L square, so we have 3a L cubic column, this is the total positive charge in all faces. The QB negative, it is equal to rho PV dV integration over volume, which is equal to rho PV, it is minus 3A dV, it is dx dy dz, integrating all from minus L over 2 to L over 2. So the volume of the cube is L cubic column. Now QB total equal to QB plus QB minus, which is equal to 0. That is, the material is neutral. The material is electrically neutralized. So breaking down does not have been affected to the cube.